Hello?
Question. Just homeworks now or in this section?
In this section, it's fine. Yeah. Sorry, I don't know. You can just fold it up. Okay. All right. The homework folders are around, so you can put your homework in the box. Just make sure it's in the right TA. Any questions about the homework today? Or just today? Is it okay? All right. Doable. Okay. So yeah. Yeah. I can't hear the question, sorry. The word explanation is better. I mean, you don't have to spend pages and pages. But just, that way you have a little bit of justification. Any other questions about homework 3? I put up yesterday. It's due a week from today. Okay. All right. Any questions about the homework? Remind me to bring the homework with me this time, because last week I forgot I left them in the class. So just like 120 homeworks here. At the end of class, to make sure I take them home. Any other questions? Any questions about? Yeah.
When are we getting our homework one back?
You'll get it back in section.
Okay. Okay, cool. Thank you.
Any questions? Okay. All right. Okay. All right. So there's homework 3. It's due in a week. Okay. Does anybody want to bid on John Nash's Nobel Prize medal? Did you see the thing? It's funny.
Why is it up for sale?
I think his descendants wanted to divide up the proceeds, essentially. So, yeah.
I thought it was like insulting or something.
No, I think he's okay, yeah. Okay, so we have 2 methods of making a prediction in a strategic form game. What are they? First one we did was what? Well, iterative elimination of dominating strength, exactly. And then the second one was Nash, right? Okay, so are we done? Apparently not. Not quite. And then why? We showed a clip at the end of the last class, which is what? Did you guys, we had no idea what that was? That's a soccer game. It's a game which more people in the world play than any other game. Right? It's the most guess what the second most popular sport in the world is? In terms of it's badminton. Yeah, it is. It is badminton, yeah. You don't believe me? No, there's like this 300 million Indonesians who play badminton. Okay, anyway, in India, of course. All right, so let's try to model that game as a soccer game. What were they doing in that soccer game? The penalty kick shootout, right? Okay, did you recognize some of the players, by the way? It's a while ago. Some of the players look like Zabi from... Yeah. Some are very well known. Okay, so this is what's going on. I give up. What's going on in a penalty kick? Okay, so let's analyze in terms of game theory thing. What's the first step? Players. Who are the players? The shooter and the goalie. Okay. And then what are their actions?
Catch the ball.
Catch the ball, not catch the ball. Kick it or not kick it?
No, I think it's make it into the goal.
No, I mean, does it?
It's the ball or not into the goal.
No, but yeah, go ahead.
It's either
trying to shoot left or right.
Kind of, exactly right. Obviously, you're going to kick it. You're not just going to go off the ball and say, sorry, I'm not going to kick it. Whatever. You're going to make a decision about where to kick it, right? Which direction, okay? So roughly speaking, it's left or right. That's essentially what it is. It means you can maybe do high or low, but it's basically left or right. So so what are the, I'll call it a strike, what are the strikers' decisions?
Oh, so this is both.
Left or right? What about the keepers?
Left or right.
Essentially left or right, okay? No, so we'll simplify it. So I'm going to do, instead of left and right, I'll do east and west because it's a little bit less confusing because the keeper's left is the striker's right, et cetera, et cetera. So let's just make it east or west, so they're absolute directions. This is my game, so let's fill in the payoffs. That's the third thing. Okay, so what goes in here? This is where the keeper goes east and the striker goes east.
Lose for the striker and aim for the keeper.
Yeah, this is where the keeper wins, right? So the keeper successfully defends and the striker loses, yes? Okay, makes sense. How about here? This is where the keeper goes east and the striker goes west. What does the keeper do? This is where the keeper loses. The striker wins. This is where the keeper goes west and the striker goes east. Keeper loses and the striker wins, right? Striker puts it in an empty goal. The empty part of the goal. Okay, and here the keeper goes west and the striker goes west. What happens here? Keeper wins. Have we seen this game before?
Chicken.
It's not chicken, yeah? Is it a Princess Dilemma? No. We have seen it before though. Matching pennies, yeah? Or also the D-Day one, you know, right? Okay, matching pennies. All right. Okay, so let's try to find Nash equilibrium. Oh, I give the answer. Let's try to do this. If the striker goes east, where does the keeper want to go? East, right? So I'll put a little star there. Oop, we'll make it red. If the striker goes east, where does the keeper want to go? West, because 1's better than 0. Okay, how about the striker's best response? If the keeper goes east, where does the striker want to go? West, right? Keeper goes west, where does the striker want to go? East, right? The striker wants to go in a different place from where the keeper is. Okay. Is there anything which has both a star and a plus? No. Is there a Nash equilibrium? Is there? No. So what do we do? Just give up. Say we don't know. Okay. Then just quit it and say it, whatever. Okay. But actually, let's try to be a little more ambitious than that. So let's say that we don't quit. We actually said we're saying we're going to try to make a prediction. What do you think that prediction would be? And in real life, what do you think actually happens?
They maybe consider the tendencies.
Oh yeah, okay, so
determine
right.
what they do.
Well, first of all, they have like scouting reports on that, right? So these people are really well known. They, you know, a lot of people. So people will, the scouts will say, "Hey, that guy tends to go to the left." Or when it's his birthday, that person tends to go to the right. And do all these things, okay? But yeah, in addition to that,
Practice more.
practice. There's this guy named Balotelli. Have you heard of this guy? So he's like super really good at faking and like he has like a very high hit rate for penalty kicks. But more basic than that, what do people actually do? So what do they not do? Let's think about what you do. If you're a goalie, are you going to like play this all the time?
No,
No. Are you going to go east all the time? Why don't you go east all the time?
because if you're predictable, you know.
Yeah, of course, because then what will the striker do? Just go west all the time, right? So are you going to do anything with certainty? No, right? Because if you do anything, how simply with the striker, are you going to do the striker, are you going to do anything with certainty? No, right? If you do the striker and you go west all the time, what is the goalie going to do? He's going to go west, right? So what do you do and what do people actually do in real life when they play this game?
They read the shooter.
They read the shooter a little, well, I guess so.
You can read the.
You can? I'm looking for, yeah.
Even if you're random, it's very difficult to spot, develop a pattern in your randomness.
That's true.
You split it 50-50.
Yeah, you kind of, okay, people are basically saying, so you basically randomize, okay, right? It's important, the last thing you do is be certain. And you're right, to some degree you can read, so for example, Balotelli's supposed to be really good at reading and reading and stuff. But what you do is randomize, right? You want to be unpredictable. Like if you're finding D-Day, the last thing you want to do is tell the Nazis, by the way, we're going to go on Normandy. Okay? You want to randomize. Right? You want to be uncertain. All right. So what we're going to do is do this. We're going to add the 50-50 strategy. Why 50-50? Let's just put it in there. So what do? We're going to add another strategy. We're going to 50-50 strategy in there. By 50-50, I mean randomizing between going east and going west. Sometimes I'll go east, sometimes I'll go west. So when we actually see people play these things, okay, so I expanded the game. Before I had just two strategies for the keeper. One's going east, one's going west. That was 50-50. Similarly for the striker, I had two strategies before, now I add this strategy. Okay? So this is not a big deal. The only thing I have to do is figure out how to fill in those numbers. Okay? So for example, what are the payoff numbers there? This is what happens, for example, if the keeper goes east and the striker goes 50-50. Okay? All right, to fill in those numbers, I need to take a little bit of an offshoot interlude kind of thing. Okay? Does everybody have an idea about how to do this? How would you fill the numbers?
1/2.
Why would it be 1/2 now?
Because your chances of actually being within range are half of what they were if you
Yeah, that's a good notion, exactly. Does anybody else have something? Yeah. Yeah, exactly right. So it has something to do with the probabilities, right? So if the striker goes east, here, say we're figuring out this. The striker goes east half the time, west half the time, right? And we're saying the keeper goes east. So it's sort of given this, how often is the striker going to win? Half the time, right? How often will the striker lose? Half the time. So we can use those probabilities along with the payoffs to kind of come up with a new payoff. Right? Yeah.
In terms of predicting their randomness, that would be a preferred position, so you could expect them to be in that position frequently.
Yeah, we'll go into that. Okay. Any other questions about this? So what we're going to do is think about how these payoffs kind of interact, all the probabilities interact with each other, and then come up with a payoff. Anyway, so we'll do our little interlude. How do we fill in payoffs? So we have a little interlude called probability and expected value. And you may have seen this before. We'll just go over it. What is probability? The probability of a random event is simply the likelihood it will happen. What is a probability? It's a number between 0 and 1. It can't be a negative probability or a probability which is like 3. For example, no one says there's a 120% chance of rain today. If you add up probabilities over all possible events, you get 1. So you can't have a 30% chance of rain, 30% chance of snow, and 50% chance of sun. It has to add up to 1. So for example, today is a 20% chance of snow, 50% chance of rain, and 30% chance of no precipitation. So probabilities are just a bunch of numbers which are bigger than 0, bigger or equal to 0, and add to 1. Any questions about this? Have you seen probabilities before? So let me give you an example. This is roulette. Say you drive 2.5 hours to Las Vegas. You can see one of these things. Okay. What's the probability of balls landing in this 26? You know, they spin these things around. The ball will not land in there. What's the probability of that happening?
How many slots?
Well, you have to count it exactly. How many slots are there? Okay, well, there's numbers 1 through 36 plus there's the 0 and the double 0, yeah?
So 1 out of 30.
So there's a total 38, yeah? Okay. So what's the probability it ends up in this one of them? 1 out of 38, exactly. By the way, if you go to Monaco, would you get the same deal? Have you ever gambled in Monaco? No, seriously. If you gamble in Europe, there's only 1 green. In Las Vegas, there's 2 greens. So, just letting you know. Yeah. Yeah, exactly. People in Las Vegas are a little greedier than okay, so the probability of landing in 26 is 1 out of 38. Okay. What's the probability of it landing in red? Well, we just count the number of red ones, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. It is how? 18. I think there's 18 red ones. Did you count them? There's basically all the odd numbers. There's 18 of them, like 1 to 36, 18 of them. And so the total number of things is 38. So the probability of the ball landing in red is what? 18 out of 38. How about the probability of the ball landing between 1 and 12? 12 out of 38. All right, does it make sense? Okay. All right, now this is what, if you go to Las Vegas and put your money on the board, you buy some chips and you put your chips on these things. Okay. If I put $1 on red, so I put a little dollar chip and put it on red like here, what is my average payout? Okay, so sometimes I'll get 0, sometimes I'll get 2, right? Have you ever gambled? And I've never actually done it on myself, I've just seen it on television or the movies or whatever. Okay, you put a chip on red, and if you win, if it comes up red, you get 2 back. Yeah? Okay. So what's your average payout going to be? Well, you'll get 2 sometimes, right? How often will you get that 2? We just figured it out. 18 out of 38 times, right? It's 2, that's, you get a prize of 2 with probability 18 out of 38. Yes? And sometimes you'll get a 0. How often will you get the 0? Huh?
138.
What?
Is it-
No, I'm sorry. Not get the 0. They get nothing back.
20 out of
20 out of 38, right? Exactly. It's the 1 minus 18 over 38, right? The possibility you'll lose is 20 out of 38. Okay? So the probability of red I win is 18 out of 38. Okay? The probability of some other color that is I lose is 20 out of 38. So over time, if I play this over and over again, I will get this.
More often you'll lose.
You know, I'll get this. I'll get $2 with this probability and $0 with that probability, right? Okay, so if I win, I get $2. If I lose, I get $0. So overall, I will get this on average. Okay, does that make sense? This is what I get if I win. I'll get $2 if I win. This is the probability that I win. This is what I get if I lose. This is the probability I lose. So it's 2 times this, 0 times this. This number is 36 over 38. It's 0.15. Does that make sense?
What does the 0.95 represent?
This is how much I'll get back for making this gamble. Okay? 18 out of 38 times I'll get 2. 20 out of 38 times I'll get 0. So average over all those things, it's 36 over 38, and it's 0.95. Okay, why is this number less than 1? Exactly. So that's why the reason that there exists a gambling industry is because this number is less than 1. They make 5% basically on every gamble. Okay. Does that make sense? Few more examples? Okay. Any questions about this? Puzzle books? So the expected value, so to speak, is 36 over 38. Okay, that's how much your expected value is when you put $1 in. Okay, so let's just sit down. The expected value of a gamble is the probability of the event times the payout from that event summed over all events. So if you want to find the expected value of a gamble, you do this. For example, if you think about putting some money in the lottery, it's like $36 million times the probability of getting it. Right? Is the expected value from the lottery usually less than the lottery ticket, or is it more than?
Significantly less.
It's much less, yeah. There's some cases, some historical times where it was actually higher. Like it's sometimes like a Powerball or whatever, but usually it's much less. It has to be much less because they wouldn't make money on it. Okay, does it make sense? Expected value is just the probability of the event times the payoff from that event, summed over all events. Okay, so for example, the expected value of betting on red is 36 over 38. That's what we just did. What's expected value of betting on 26? Okay, let's go going back. If I put like a little thing on 26, if I win, does anybody know the payout if I win?
38 or 36?
I think it's 36, yeah.
36.
You get, so if I put a chip on 26 and it happens to land on 26, I'll get $36 back, which is a good deal. Okay.
That's not much.
But it's a very low probability thing. So if I put a chip on 26, I'll get $36 back, but with this probability, 1 out of 38, right? I'll get $0 back with this probability. So I calculated it all together, it's 36 over 38. Does that make sense? How about if I put a chip on 1 to 12? Has anybody ever done that?
3 times.
Huh? You get 3 times, exactly. If I put it on 1 to 12, if I win, I'll get a 3 times payout, $3 payout. This is the probability of it going from 1 to 12. This is the probability I lose when I get 0. You cool with this? Is it okay? All right. So, for example, today there's a 20% chance of snow, 50% chance of rain, 30% chance of no precipitation at all. Say my payout from snow is 10, My payoff from rain is minus 20, and my payoff from no precipitation is 0. What's my expected payoff from my expected utility? Remember, the expected utility is simply the probability of each event times the payoff from each event added up over all events. Huh? Negative 8?
Yeah.
Okay, how did you do that? Just did a lot of math in your head quickly. Just tell me.
Just add them up.
Yeah. So I'm doing what? 10 times what?
10%.
Yeah, my payoff from snow is 10, and I multiply it by times 0.20, right? My payoff from rain is minus 20, and I'm multiplying that by what?
A half.
Half the 50%, and 0 times 30%. So it's what? Yeah, 0.20 times 10, 0.50 times minus 20, plus 0.30 times 0, which is minus 10. Make sense? Okay, so this is how I create payoffs from random events. All right. Any questions about this? Before we go on? This is my little interlude. Okay. All right, so now we're sort of set to fill in this table. So let's do that, what we were talking about here. So let's do this one. Let's fill in this one. This is where the keeper goes east. Let me write down the original name. So keeper goes east. Okay, so if the keeper goes east, and when the striker goes 50-50, look at brief, this is the so if the keeper goes east and the striker goes 50-50, what happens? Okay, so we're trying to fill in that little square there. Oh, that guy right there. Okay, so the keeper goes east. Oh, I'll make a little picture too. Let's see. Here's my keeper. So the keeper can either go east or west. And the striker can also go east or west. Okay, so the keeper's going east, and the striker's going east, probably half, and west would probably half. So the keepers go east all the time. Okay, so what actually happens? With what probability does the striker, if the striker goes west, what happens? So, well, let's do it one by one. Let's do the keeper's payoffs first. So the keeper's going east. Okay, if the striker goes west, what is the keeper's payoff? 0, right? So keeper 0 times what? What's the probability the striker goes west? 1/5. If the striker goes east, what happens? The keeper wins, right? The keeper gets 1, right? What's the probability the striker goes east? 1/2, right? So this number altogether is what? 1/2. Does that make sense? This is what we said before. So the keeper's going east all the time. The striker's going west 50% of the time, east 50% of the time. The keeper wins half the time. Gets the 1/2 the time, and gets 0 half the time. Altogether, the keeper gets a half. So I'm going to put it in half. Okay, what about the striker? Okay, then the keepers go east all the time, the striker's going west half the time, and east half the time. If the striker goes west, the striker's payoff is what? 1, right? The striker wins. What's the probability that happens? 1/2. If the striker goes east, what happens? The striker gets 0. What's the probability that occurs? 1/2. number is what? Okay, any questions about what we're doing? Yeah.
Couldn't you just figure out one and know that the other one's the remainder?
Yeah, that's true too. Yeah, you could have done that thing. It's sort of zero sum, right? So you could have simply said, if the keeper's payout is 0.5 and the striker's is just 1 line. Yeah. Yeah. Sure, of course. There's another one. Okay, I thought there was. All right. All right, so clear what we're doing? Let's try to fill. Let's want to fill in this one. Let's fill it out. Here's where the keeper's going 50-50. And the and now the striker's going east all the time, so the striker's going east all the time like this. Okay, striker's going east all the time. What's the keeper's payoff? If the keeper goes west, the keeper gets what? 0, because the keeper misses. That happens with what probability? If the keeper goes east, what happens? The keeper wins. And this number is half. How about the striker's payoff? The strikers go east all the time. If the keeper goes west, what's the striker's payoff? 1. If the keeper goes east, the striker gets what? 0. And this number is? So that number 2. Okay, how about this one? Do you want to do it all over again? No. What's this going to be? Half-half, right? Similarly, how about this one? This is also half-half. Okay. This one in the middle is slightly different. This is where they're both going 50-50, right?
Keeper wins, right?
Well, let's see what happens. Just calculate it. So they're both randomizing. Okay. So if the keeper goes west and the striker goes west, what's the probability of that occurring?
50-50.
Okay, so the keeper goes west and the striker goes west. 1/4, right? Because that's probably 1/2 times 1/2, right? So that's 4. If the keeper goes west and the striker goes west, what is the keeper's payoff? 1, right? Because the keeper won, right? The keeper blocked the shot. If the keeper goes west and the striker goes east, what's the probability of that occurring? 1/4. What's the keeper's payoff in that circumstance? 0, right? If the keeper goes east and the striker goes west, what's the probability that occurs? 1/4. If that happens, what is the keeper's payoff? 0. And finally, if the keeper goes east and the striker goes east, what's the probability that occurs? 1/4. And then the keeper's payoff is going to be 1. What's this number? It's 1/4 plus 1/4, which is 1. Want me to do the same thing for the striker? No, it's just a half. Okay. All it is just 1/4. It's the same. 1/4 times 0 plus 1/4 times 1 plus 1/4 times 1 plus 1/4 times 0. Yeah. Is that okay? Okay. So this is a half. Keeper gets a half. Striker gets a half. Okay. So what did we do? The original game there was no Nash equilibrium, so we said, well, in actuality, in the penalty kick game, people randomize, right? They don't do anything for certain. So we're adding that extra strategy. We're adding that 50-50 strategy in there. Okay, so now in this new game, can I find any Nash equilibrium?
Isn't the center one Nash?
Yeah, I think it is a center. Let's see. Let's just do the stars and pluses thing. Okay, if the striker goes east, if you're the keeper, what are you going to do? You're choosing between 1.5 and 0, right? So what are you going to do? Yeah, you definitely go. Hold on. If the striker goes east, you're going to go east. Yes. Yeah, you want to block the striker. Right? If the striker goes 50-50, what are you going to do? Yeah, all of these are tying for first place, yes? They're all good. Okay. See, look at my- If the striker goes west, where does the keeper want to go? West, because 1 is the biggest number. Okay, fine. This is the keeper's best response. How about the striker's best response? If the keeper goes east, where does the striker want to go to? West. Right? If the keeper goes 50-50, where does the striker want to go? They're all, tying for first place. If the keeper goes west, where does the striker want to go? East. Right? Okay, so is there a Nash equilibrium? Is there anything with both a star and a plus? Yes. So where's the thing? Oh, it's this. Okay, so the Nash equilibriums, they both go 50-50. Do we actually see this in real life? I know we do, right? I mean, if you didn't do 50-50, say that you're like a 60-40 person, so 60% of the time you go east, 40% of the time you go west, would you survive for very long? No, right? What would happen? So I'm the striker, right? 60% of the time I go west, 40% of the time I go east. What's going to happen? Yeah. The scouting report will come back. Yeah, and they'll say, hey, that guy goes 60% of the time west, so just go west. Yeah? Right, so I'll be much less effective, right? I really need to become as close to 50-50 as possible. Yeah? If I have any tendency at all, people will pick up on it. Yeah, and you see that? Okay. So yeah, it really will be 50-50 as much as possible. Okay. So this is nice. We had a problem where we didn't have any Nash equilibria, but we added more strategies. We added the strategy of 50-50. By adding the strategy, we then had to figure out how to fill the payoff. So once we did that, we were able to find the Nash equilibria. Questions about that? Okay, so in some sense we kind of cheated a little bit. There was no Nash equilibrium of the original game. So what we said is we're going to change the game. We're going to add another strategy, a randomized strategy. Once we add that strategy in, we can find the Nash equilibrium of this bigger game. Okay? And if I write it in words, it's the Nash equilibrium is the keeper goes east is probably 5, west is probably 5. Striker goes east is probably 0.5, west is probably 0.5. Okay? Any questions about that? No?
Have they surveyed players and see if they think like that?
That's a good question. There is one of my former colleagues did this thing. He actually looked at like many penalty things. So I'll send you the paper. I'll send you the thing about the animals too. I'll send it out. So actually, the people found that people don't kick in the center enough. Apparently, kicking the center is actually much better than you think it is. So, when I was an AOX head coach, I was an AOX head coach for my kids. Like when they're 8 or 9 years old. One interesting thing they say is that you have a very strong instinctive urge to kick the ball at a person because you're passing all the time. You have to teach the kids, don't kick it at the person because unless you tell them explicitly, even right in the goal, it's just so hard not to kick it at the person. It's funny, yeah. Okay. All right. But yeah, I'll send you that paper. If you have time, I'll Google it later. We can. So people have done like serves, tennis serves, like how random is that? Okay. So, any questions about this? So, this is what we call this is mixed Nash equilibrium. Before we had so-called pure strategy Nash equilibrium. This is randomized strategy Nash equilibrium. Sometimes people use the word mixed strategy Nash equilibrium. This is what's on the homework grade. So, what we're doing in mixed strategy Nash equilibrium is we're adding a new strategy and figuring out the offsets, trying to find the match. Okay. So, any questions? One of the problems, though, what we just did is what we did was pretty simple and relatively easy to understand. But there's a problem, which is that we kind of lucked out. We put 50-50 in there, but how do we know it was 50-50? We just sort of guessed, right? Maybe it's 60-40, 49-51, or something like that, right? How do I know? well, in this case, I just happen to guess right, but I really need to include all possible randomized strategies, right? I need to include 99.1, 98.2, 97.3, 96.4, whatever. So the way I do that is I make a little diagram like this. Okay? So I do a P here and 1 minus P here, and a Q there and 1 minus Q. What does this mean?
Probability.
Yeah, there's a probability. So this P is going to be a number between 0 and 1. This stands for the probability that the keeper goes east. And so since they add up to 1, this has to be 1 minus P. So for example, if P is 2/3, this number is 1/3. This P stands for my strategy. It's how much, in this case, how often I go east. Q is the probability the striker goes east. And 1 minus Q is the probability the striker goes west. So we're going to now consider all possible P and Q, not just 0.5. Okay. So say keeper goes east with probability P and west with probability 1 minus P. The striker goes east with probability Q and west with probability 1 minus Q. So we're going to let these be variables. Okay. So what does the game look like with all possible randomized strategies? So it's going to look like this big box. Okay, so I can use, like, for example, a big Excel spreadsheet. And I'm going to say P equals 1 to P equals 0. So up here it means, think of this as like a huge spreadsheet with like hundreds or thousands of entries. So this is like P equals 1. This means I go, what, east all the time. Okay, so this means I go west all the time. Okay, maybe I'll put my P and Q over there. So P equals 1 means the keeper goes east all the time. P equals 0 means the keeper goes west all the time. That means the keeper goes east. P equals 0 means the keeper goes west. What if P equals 0.5? What does that mean? 50-50? Is that, what if P equals 0.9? What does that mean? Yeah, the keeper goes east 90% of the time and west 10% of the time. 1 minus 0.9. Yeah. Okay, so if I choose a strategy up here, it means I'm going east all the time. This means I'm being east 99% of the time, 98, 97, 96.5. Here I'm going west most of the time. Here I'm going west all the time. Okay? Let's do the same thing for the striker. The striker can either go Q equals 1, which is east all the time. If Q equals 1, that means the striker is going east all the time. If Q equals 0, that means that number is 1, right? The striker is going west all the time. If Q equals 0.5, that means striker is doing okay, so if I have a big Excel spreadsheet, I can do this, right? I can make this like hundreds of little entries here and hundreds of little entries here, all corresponding to different strategies. Okay, and I can fill in the payoffs, just basically a more complex version of what I just did. Okay, with a not to turn the 2 by 2 into a 3 by 3, but I can turn the 2 by 2 into like a million times a million. Okay, should we do that? No, that's going to take too long. How do we fill all the payoffs? We're just not going to do that. Okay? This is too much work. Okay? But what we can do is we'll just fill in the stars and pluses, just the best responses. Okay? That's great. Yeah?
How would we fill this and include it? Because it seems like this is all inclusive in the way that if the striker goes west and the keeper goes west, it looks like they're going to be 0.
So if the keeper goes west, the striker goes west right down here, you mean?
Yeah.
Yeah, so I would put a payoff here. If I did this, if I made a really big matrix, I would put a payoff here.
So would it also be the one bottom right corner then?
Okay, so what would let's say what's the payoff here? This is where the keeper. So this is the name of the strategy. Okay, P equals 0. That means the keeper goes west all the time. Q equals 0 means the striker goes west all the time. They end up here. If the keeper goes west all the time, the striker goes west all the time. What is the payoff? Yeah, exactly, right, exactly. So I would put like a little 1-0 there. Okay? What would it be here? I have to do some calculation, right?
So those are
Yeah, exactly, these are not payoff numbers.
yeah, okay.
Yeah, exactly, right. They're the name of the strategy. Any questions? No.
How do you set an interval for the in-between to know which are the best responses? Like, will you give us one, or do we just have to kind of?
Okay, exactly, right, so in those penalty kick them, we just guessed one, and it happened to work, right? So, in general, that won't work, because how do I know? So, what we're gonna do is figure out how to find that, exactly, that's exactly what we're gonna do. Okay, so, I'll give you kind of the long, fully drawn out answer, but once you understand it, then there's a short way. All right, anyway, the point is, we're not gonna film this huge table, too much work, we're just gonna film the best responses, the stars and pluses. Okay, remember what we did here before? Here, again, we made this larger table, and then we did the stars and pluses. Okay, so we're not gonna film the numbers, we're just gonna do the stars and pluses directly. Okay, so let's do that. What's the keeper's best response? Okay, so let's do some examples. If the striker goes east all the time, striker goes east, that means the striker is choosing this column here, okay? The keeper could go east all the time, east half the time, west all the time.
What is
Okay,
good strategy?
what's the best response for the keeper if the striker goes east all the time?
To go east all the time.
To go east all the time, yes? Obviously to cover. Okay, so therefore I'm gonna put a little star there. Okay? That's the keeper's best response. Of all these possible things, that's the one, that's the cell which has the highest number. What if the striker goes west all the time? Which of these cells will have the highest payoff for the keeper? What will the keeper do if the striker goes west all the time? Go west all the time, so I should put it from there. Yeah? Okay, now we're not quite done. What if the striker goes east 99% of the time? That is almost all the time.
You should go.
The keeper should what? Always go east, yeah? Make sense? Yeah, if you think the striker is going to go east 99% of the time, we'll just cover east. Okay, so of all these things, the best one is that. So the keeper will go east. Okay, what if the striker goes west 99% of the time? What is the keeper going to do? Go west all the time. Does that make sense? What if the striker goes east like not 99% but 95% of the time? What is the keeper going to do? Always go east, right? Yeah. Why always? Yeah, right. You just go to where the better odds are, right? Okay. Okay. Similarly, if the striker goes west, 95% of the time, what is the keeper going to do? West. So we have this little picture here. So this is kind of interesting. So the striker is going east. The striker goes east all the time. The keeper will go east. The striker goes east 99% of the time. The keeper will go east. The striker goes east 95, 94, 90% of the time, 80% of the time. The keeper will still go east. So the striker is going 85, 87.
75, would that be the point?
Maybe
where
this is
it starts
75,
going
whatever.
down?
Yeah. At some point, the keeper switches over from covering east to covering west. Yes?
Yeah.
Right? That's the interesting part, right? At what point is that? 50-50, right? Make sense? Okay, so think of it this way. This is just like, now the striker is just going like east maybe 60% of the time and west 40% of the time. The striker goes east 60% of the time and west 40% of the time. What is the keeper going to do?
You should go east.
Always go east. Yes?
Yeah.
Okay. Does that make sense? No? Why not?
Because I would start transitioning to center around 75.
You would? Oh, but there's no, first of all, center's not, there's no center. It's not, you have to do like.
Is there a center here? There's 50-50.
Oh, okay, that's a good question. Okay, so say, why is it, okay, so here's saying the striker is going like 60% east, 40% west. And I say, if you're the keeper, why don't you do like 50-50?
That's what I would.
That's what you do? Okay, I'm trying to think, but what's the argument for doing that as opposed to, why would you do that?
Because the odds would be more in your favor for the 40% when he's going the other way.
Okay, it's true, so, okay, so right, this is where the striker is going 60-40 and I'm gonna go 50-50. So you're right that I might sometimes get the 40%, right? I might sometimes win if he goes west, whereas I'll sometimes win west, right? But think of it this way. If the striker is going east 60% of the time and west 40% of the time, if I go east all the time, what's my probability of winning? 60%, right? If I go west all the time, what's my probability of winning? 40% of the time, right? So if I go east, my probability of winning is 60%. If I go west, probably is 40%. So should I ever move a little bit from going east to west?
At some point, I think you should, yes.
At some point, but not when it's 60-40, right? Do you want me to do the math for you?
I agree if those are all the options.
Yeah, but that's, the options are, okay, the options are choosing.
I thought we were
Yeah.
talking about the space in here that.
Yeah, okay, no, okay, think of it this way. Okay, the keeper's going east, sorry, the striker's going east 60% of the time, west 40% of the time. If I cover east, I'm the keeper, I'm going, I win 60% of the time. If I cover west, I'm winning 40% of the time, right? So therefore, every time I cover east, that's better than if I cover west, right? Does that make sense? So therefore, I should never cover west at all. Anytime I'm covering west, I should be, always have a little bit better chance if I cover east. Make sense? The only time when I'm indifferent is when what? Somebody said already? Is when the striker does what? 50-50. Okay. So right at 50-50, then the keeper, what is my best response? And you either cover east or west or what? Anything, right, for that matter, right? It's this whole thing.
But isn't there a degree of probabilities where it could be 50-50? Is it exactly that?
Again, think of it this, let's take this. Say the striker is going east 51% of the time and west 49% of the time. Okay, what would you do? Would you sometimes go west? No, because we can talk, I'll do a spreadsheet if you want. I'll do it at home. Okay. I'll share the spreadsheet at home. I'll do it. Basically, even if somebody's slightly off, just a hair off to 50-50, you want to cover what their bias. And you want to cover it 100% because you're getting a better deal that way. Okay? Does that make sense? Better deal. I'll show you the spreadsheet. I'm tempted to do it now. Let's just wait. Anyway, Q goes 0.5. You're exactly different. Why is that? If the striker is going half east west. If I cover east, what's my probability of winning? 0.5. If I cover west, what's my probability of winning? If I go 50-50, what's my probability of winning? Alright, so no matter what I do, I'll win with probability of 0.5. Right? Yes, okay, thank you. Okay. Does it make sense? This is person one's, the keeper's best response. It switches over from going east to going west. The striker goes east all the time, or most of the time, the keeper will go east. The striker goes west all the time, or most of the time, the keeper will go west. The keeper will switch over exactly when Q goes 0.5. How about the strikers? So that's what I call the simple switchover probability. This is where the keeper switches over from east to west. What about the striker's best response? If the keeper goes east, what's the best thing for the striker? Where does the striker want to go if the keeper goes east? Oh. So if the keeper goes east, the striker wants to do west, right? So we're going to put a little plus in there. If the keeper goes west, what does the striker want to do? Which is the best number of all these things? East, right? So we're going to put a little plus there. All right. If the keeper goes east, most of the time, like 99% of the time, where is the striker going to go? West. Right? If the keeper goes west, 99% of the time, where is the striker going to go? East. Right? So you have a similar picture. Okay. At what point does the striker switch over from going east to west? Exactly 50-50. You guys, I'm sensing a little disbelief, skepticism. let your skepticism be known. Do you want me to do the spreadsheet? You want to see the spreadsheet? Sure? Oh, okay, I'll do it. I'll take a little while. Okay, I'll do it this way, then I'll do the spreadsheet way. So then you'll be able to do it. Yes?
Is it because like humans don't really think in numbers, so like our moves aren't as predictable? Because like she was saying, like if it's 75%, she would go towards the middle, but like this isn't the way people like think.
No, we're all just, this is not psychological or anything, this is just straight up game theory.
Okay.
All we're doing is we're just considering different kinds of strategies here. I mean, so, all right. I'll do my way, then we'll do the spreadsheet way, then hopefully I'll convince you. Okay, anyway, this is the striker's best response. How do I find Nash equilibrium? Combine the two, okay? This is the keeper's best response, this is the striker's best response, and I have this unfortunate swastika diagram. And at least I made it go left. Sorry, there's no other way to do it. And anyway, you see swastikas and Buddhist stuff and Hanukkah stuff anyway, but where is the Nash equilibrium?
The center.
The center, right? That's the Nash equilibrium. Okay? So what did we do? We basically just did the same thing twice. The Nash equilibrium is in which what happens in the Nash equilibrium?
The point.
Yeah.
They said
Both people are doing what?
same thing.
50-50, right? I wrote down sideways. This is the same as what we did before, but the difference is that before we just considered one exit strategy. Now we consider them all. Okay, so there's no arbitrariness. Okay. Any questions about that? Okay. So this is the next one. Let's do another example. Okay? Let's get this game here. Okay. How do I find the Nash equilibrium of this game? If 2 does A, what's 1's best response? 4 or the 1, which is bigger? 4. If 2 does B, what's the best response for 1? 6. If 1 does A, what's 2 does response? 3, which is a 3. And if 1 does B, 2 best response is to play A and get the 7. Okay, is there a Nash equilibrium? No. So, there's no strategy Nash equilibrium. How do I make a prediction? I have to consider randomized strategies. Okay, what strategy should I add in? Should I do 50-50?
No,
Who knows,
not
right?
50-50.
Exactly, that's I don't know. Okay? So what we're going to do is the same thing we did before with that box. Okay? So there's no good strategy Nash equilibrium. Let's consider so-called mixed strategies. So what I'm going to do is put my Q's in there. Okay. How do we consider these strategies? Well, I'm going to make this box again. Okay. Q equals 1 is where person 2 plays A all the time. When Q equals 0, person 2 is playing B all the time. When P equals 1, person 1 is playing A all the time. When P equals 0, person 1 is playing B all the time. What's person 1's best response? If 2 plays A, that is Q equals 1, that is this is being played all the time, what does 1 want to do? So 2's playing A all the time, what's 1's best response? Well, 1's choosing between 4 and 1, so 1 wants to do what? A, right? So I'm going to put, where am I going to put the little star thing? At the top bit. If 2 plays B, that sets Q equals 0, so that number is 1. What is 1 going to do? 1's choosing between the 0 and the 6, and 1's going to do what? Play B, right? If 2 plays A most of the time, what is 1 going to do? So most of the time, 2 is playing this. What does 1 want to do? Play A, right? Okay. If 2 plays B most of the time, what does 1 going to do? Play B. Okay, etc. And the whole pattern is going to, right? The same as before. The question is, when does 1 switch over from playing A to B? Okay? So 2 will first, so if 2 plays A all the time, 1 will play A. If 2 plays A most of the time, 1 will play A. If 2 plays B all the time, 1 will play B. If 2 plays B most of the time, 1 will play B. As this probability changes, person 1's best response will suddenly switch over from A to B. At what point will that happen? Okay, that's the question. Before it was 50-50, but who knows what it is now. Okay, what's the switch over? So, what's the switch over Q for person 1? Let's think about this. Remember that person 2 plays A with probability Q, and B with probability 1 minus Q. If person 1 plays 1A, what's his expected payoff? If he plays 1A, he gets 4 with probability Q, and 0 with probability 1 minus Q. Okay, right? So we're assuming that person 2 plays this with probability Q, plays A with probability Q, and plays B with probability 1 minus Q. If person 1 plays A, he gets 4 with probability Q and 0 with probability 1 minus Q. Okay. So what is the expected payoff of all that together? It's 4 times Q plus 0 times 1 minus Q. Okay, and that number is going to be what? It's 4. Okay. If he plays B, what's his expected payoff on the B? Again, we assume person 2 is playing A with probability Q, B with probability 1 minus Q. If person 1 plays B, person 1 gets this 1 with what probability? Q, and gets the 6 with what probability? 1 minus Q. Okay. So his expected utility is 1 times Q, 6 times 1 minus Q. Which is, so we do a little math, that's 6 minus 1. Okay. Are you with me so far? Yes. Okay, if Q is 1, which is the bigger number here? If Q is 1, that number is 4, what's that number? 1. Yeah, go ahead.
Can you explain why we're doing like the Qs? Because isn't it player 1?
Yeah, so okay, we're looking at when 1 switches over from A to B as Q changes.
Oh,
Okay? Right. It is a little confusing.
So when we
Okay.
do Q, we are working with probability B.
Yeah, exactly. We're looking at when 1 switches over, and 1 will switch over at a probability for person 2. Just think of the penalty kick. I switch over from east to west when you do exactly 50-50. Okay. If Q is 1, then my best response is to play A. Okay, that's what this was. If Q is 1, my best response was to play A. Oop. What happens when Q is 0? Which number is bigger here? 4Q or the top or bottom? Bottom. If Q is 0, this is 0. This is 6, right? If Q is 0, I want to play B. Right? Q is 1, I want to play A. Q is 0, I want to play B. What if Q is 0.99? Which is bigger, top or bottom? A. What if Q is 0.01? B, right? Yeah? Okay. So Q is close to 1, I want to choose A. If Q is close to 0, I want to choose B. At what point do I switch over between A and B?
2/3.
2/3? How did you figure that out?
Equal.
Yeah, you set them equal. Why do you set them equal?
Because the payoff would be,
Yeah. Go ahead.
because when the player 1 chooses A, the payoff will be exactly equal to the payoff when he chooses B.
Yeah, exactly right.
Between.
Exactly. You just saying? Another comment?
Oh, I was gonna say, it's when it doesn't matter.
Yeah, exactly right. Okay, so what you think about it is this. When Q is 1 or close to 1, this number is bigger than this, yes? When Q is 0, this number is bigger than this, right? Say Q is 1, this number is 4, this is 1. Q gets 0.99, 0.98, 0.97, 0.9, whatever. This number decreases. This number is still bigger than this, but the difference gets smaller and smaller and smaller. Finally, at some point, 1 switches over to this, right? At what point does 1 switch over? exactly when what? These things are equal. Yeah? Does that make sense? Okay. When does one switch over? When 4q is bigger than this, one plays A. When 4q is less than this, one plays B. One switches over exactly when these two things are equal. Okay? So I set them equal to each other. And I can solve and do a little math. Which you did in your head, which is 9q equals 6. Right? And then you can see why I did that. I just took 5q up here. It's q equals 2/3. Okay? Makes sense? Any questions about that? Okay, so this is how I'm trying to find that switchover thing. So to go back to my diagram. When q equals 1, person 1 wants to play A. When q equals 0, person 1 wants to play B. The switchover happens exactly at q equals 2/3. Okay, at q equals 2/3, person 1 switches over between playing A or B. Okay? Okay, let's do person 2's best response. When 1 does A, that is person 1 plays A, what is person 2 going to do? 2 chooses between the 3 and the 0. 2 wants to do what? A or B? 2 chooses the second number. It's B, right? Because 2 wants to do. If 1 plays B, what does 2 want to do? Between 7 and 2. Gets a 7 right by playing A. If 1 plays A most of the time, what does 2 want to do? If 1 plays A 99% of the time, what is 2 going to do? B, right? What if 1 plays B most of the time, what is 2 going to do? What? A, right? Okay, we have the same pattern. At what point does 2 switch over from playing A to B? Okay. What probably, yeah. You have to do a similar kind of calculation, yeah? So what's the switchover? Well, what's the switchover for person 2? Remember, 1 plays A with probability P, and B with 1 minus P. Alright. If 2 plays A, he gets 0 with probability P, and 7 with probability 1 minus P. Yeah? Again, we're taking person 1 as a constant. If person 2 plays A, he gets 0 with probability P, 7 with probability 1 minus P. If 2 plays B, what's person 2's expected utility? If person 2 plays B, 2 sometimes gets a 3, sometimes gets a 2. She gets 3 with what probability? P, right? P times P. She gets 2 with what probability? 1 minus P. So it's 3 times P plus 2 times 1 minus P. So if I math that out a little bit, that's equal to 2. All right. If P is close to 1 or 1, which is the bigger number if P is close to 1? This or this? Top or bottom? If P is 1? Bottom, right? This is 3 and this is 0, yeah? Okay. So if P is close to 1, 2 is going to play B. If P is close to 0, which is the bigger number, top or bottom? Top. If P is close to 0, 2 will play A. At what point does person 2 switch over between A and B? Huh? 7, 9? Well, how do I solve it? What do I say? Yeah, I set these two things equal, yeah? Okay. So set them equal. 2 switches over exactly when these two numbers are equal. 7 minus 7P equals 2 plus P. And yeah, I think it's I solve for P, I get like minus 8P equals minus 5. P equals 5x. Okay. So I'll go back to that picture. Now P equals 5/8. This is exactly when person 2 switches over from playing A to B. What's the Nash equilibrium in this game? Is there one?
Yes.
Yeah, it's right here where they meet. That's the Nash equilibrium. And if we were to write it down in words, it's like this. 1 plays A, because I found, so P equals 5/8. So this is 5/8 over here. This is 3/8. Because P is 5/8, so 1 minus P is 3/8. Q is 2/3, so this is 2/3. 1 minus Q is 1/3. So one place A would probably be 5/8, B would probably be 3/8. Two place A would probably be 2/3, B would probably be 1/3. Okay? This is a prediction you make. Any questions about that? This is a little bit of a tricky concept, this is Nash equilibrium, but this is what we have to, yeah. This one you mean? Oh, might be. Okay. Questions about that? Okay. All right, so this is how we find mixed Nash equilibrium. Shall I do another example? No? Can we do it? Can we go for it? Should I do my spreadsheet?
Yes.
Can I do the spreadsheet? Let's see if this is going to work. Okay. All right, let's see. Where's my Excel? Okay, here we go. I did this one. Okay, let's see. Okay. Where's my view? Okay, let's see if I can do this. Shall I do it generally? I've got it. Here, I'm gonna use, I can't see it. I have to do this. Sorry. I just bought bifocals. That's the stage I'm in life. Okay, so this is going to be ones payoffs. I'm going to make them red. Okay. And these will be am I doing this the right way? Was this so the keeper likes easy. So this is right, yeah? So this is blue. I'm going to make this blue. Okay? So this is going to be the player 1, player 2, good. All right, so now we're going to do something like a 1, so I guess, oh yeah, I'll make this P. P1. Series, linear, step value point. Oh, good, okay, good, that worked, okay. All right, make those all red. I'm gonna make my Q's this. Okay, no. Oh, well, I'll just do it manually. Okay, those are going to be blue. Okay, now how would I fill this in? This is going to be equal to what?
1,0.
It's going to be this times this. I'm going to just do plus 1 minus this times, oh, hold on. Okay, let's just make sure. Am I gonna get this right?
Program all those notes.
Oh, no, I know what I'm gonna do. I'm just gonna do this in a simple way. Okay. I'm not that good at Excel, by the way, so. Oh, this is not right either. I'll do it at home. I'm sorry. I don't want to waste everyone's time. I'll email it to you for all the non-believers out there. I'm sorry.
No, I was thinking that we're gonna use your program, right?
Yeah, you can use the program. Okay. All right, no problem. Okay. All right. Let's do an example. That's like my embarrassing moment for the day. All right. Okay, let's figure out. Is there a Nash equilibrium here? Is this a Nash equilibrium? No. We want to deviate from here. 2. Is this a Nash equilibrium? No. 1, 2, 1, deviate to 6. We want to deviate from here. 2. We want to deviate from here. 1. Right. So there's no Nash equilibrium. Oh, I'm sorry. Is this the one we just did? Yeah. So we did. Sorry. Okay. Oh. Do you want to see? Let's just do a. Okay, let me see. Hold on. Let's just do a random example. How much time do we have? 5 minutes. Okay, let's see. I want to go. Okay, let's see. Are there pure Nash equilibria in this game? Okay, is that a Nash equilibrium? No. Is this a Nash? Does 1 want to deviate? Who wants to deviate from here? 2 from here. Who wants to deviate? 1. Who wants to deviate from here? Okay, so let's try to find mixed Nash equilibria. I'll put my P here. 1 minus P here. Q here. And then 1 minus Q here. Then I'm going to make my little diagram. All right. If Q is 1, what's 1's best response if Q is 1? What is P? What is person 1 going to do? B, right? If Q is 0, what's 1's best response? A, right? Because A is better than 0. Okay, so we have this situation. What's the switch over Q? How do I find that? Okay. If person 1 plays A, I'll write it down like this. Person 1's expected utility, this is expected utility. But expected utility for person 1 from playing A is what? If person 1 plays A, person 1 gets sometimes 6 and sometimes 8. She gets 6 with what probability? Q. So it's 6 times Q. She gets 8 with what probability? 1 minus Q, so that's person 1's expected utility for playing A. What's person 1's expected utility for playing B? If she plays B, she gets 9 sometimes. She gets 9 with probably what? Q. And then she gets 0 with my probability. Okay, so how do I find the switch over Q? Set them equal, right? So let's do some math. This is equal to 6Q plus 8 minus 8Q. This is it minus 2Q. This is equal to 1. So I set them equal to each other, I get A minus 2 equals 9Q. Equals 11Q. Q is meter over 11. So at Q equals 8 over 11, comes over here. We have this. Okay?
Yeah.
Pretend that's the right. Yes?
Just on our homework, you want us to make that little box thing?
No, you don't have to do that. Okay. So, let's do person 2. We're almost done. Are we getting done to do person 2? Oh, okay. Let's just do it. I had a little bit. What's person? What's person 2's expected utility from playing A? If she plays A, what she gets? She gets 8 probability what? P and 0 would probably 1 is P. So 8, 0 to 1 minus P. That number's 8. If she plays B, what's her expected utility? She gets 6 with probability P and 3 with probably 1 minus P, yeah? This number is 6P plus 3 minus 3P. How do I find the switch over P? Set them equal. So 8P is going to be equal to 6P plus 3 minus 3P. So I have, I think 5P equals 3. Is that right? Yeah. So P equals 3/5. So what's the Nash equilibrium? Equals 3/5. So it's going to look like this. Okay. And then the Nash equilibrium will be. I'll write it down. One place, one egg, probably. What's P? 3/5. Okay, see you. See you next time. Oh, it's just well, make sure you put your homework in the box.
I have class. I have discussion.
Oh, right.
I still have like Tuesday.
That's not the audio. I never know video. Audio. Well, I'm just gonna on